Today I'm going to talk about a topic called GPU pressure measurement methods and case studies. In the past 2 years of deep optimization work, and also in discussions with many clients, we've noticed a clear trend. The demand for higher visual quality is increasing rapidly. However, when it comes to how to identify GPU pressure and how to actually solve it, many teams still have significant blind spots. So today, I'd like to share some of our practical insights on this topic. The talk is mainly divided into two parts. First, how we use a very important metric called GPU clocks to help us locate GPU bottlenecks. Second, a question we are often asked: when writing shaders, should we use if statements? Or more generally, is it acceptable to use multiple if conditions in shader code? We'll start with the first part. This chart shows the various GPU counters collected in our GPU profiling mode released last year. These metrics are obtained by integrating low-level driver interfaces from third-party hardware layers. The first and most important metric here is GPU clocks, which is what we focus on today. Its unit is called cycles, which you can think of as a way to measure the computational workload inside the GPU. Below it, there are several other important metrics that are also related to GPU performance. For example, GPU frequency, GPU shaded, which represents how many pixels we have shaded, and GPU primitive, which indicates how many triangles are submitted from the CPU to the GPU. All of these are related to GPU workload, but the most critical one for today's discussion is clocks. You can think of it as the core pressure indicator, because it directly tells us, during a frame trace, where the GPU is under heavy load and how heavy that load actually is. So let's first clarify what clocks actually means. Here is a definition from the official ARM Mali documentation. A single clock cycle can do quite a lot of work. For example, in the second-to-last line, it mentions interpolation calculations. This refers to the stage where vertex attributes are interpolated before being passed to the fragment stage. A single clock can perform many such interpolation operations. Another example is in the last line. A single clock can perform a bilinear texture sampling operation. So in short, one clock cycle can represent multiple types of GPU operations. However, it's important to note that different GPUs have different levels of capability per clock cycle. For example, on a high-end GPU, a single clock might be able to perform 5 or even more texture samples. So even though we use the same term clocks, the actual performance behind it is not identical across devices. This is an important concept to keep in mind. For a fixed GPU, if the rendering content is fixed, then the clock's value becomes a stable measurement. This is the fundamental assumption behind using GPU clocks as a performance metric. There is also another key concept. Every GPU has a maximum operating frequency, measured in megahertz. So what is the relationship between frequency and clocks? You can think of it in a simple way. 1 Hz equals 1 clock cycle per second. So if a GPU runs at 720 megahertz, it means it can provide 720 million clock cycles per second. With this understanding, we can evaluate whether a GPU workload is over budget during testing, meaning whether it can meet our target frame rate. I've summarized this into 2 lines that are easy to remember. If the per-frame clocks multiplied by the target FPS, for example 60 or 30, exceeds the GPU's maximum frequency, then the GPU, even at full capacity, cannot sustain the workload, and frame drops will occur. From here, you'll see many similar equations and relationships. Now let's look at a basic test we conducted. This test is based on a Huawei Honor overdraw benchmark, where we continuously stack full-screen semi-transparent layers. The GPU used here is a Mali G76 with a maximum operating frequency of 720 MHz. During the test, as more layers are added, overdraw increases continuously. At the same time, GPU clocks also increase linearly. Each value shown here represents a single frame. A key point appears around frame 2200. The clocks reach about 12.72 million cycles per frame. If we convert this, it's 12.72 member clocks per frame. Now let's compare it with the budget. 720 MHz divided by the target 60 FPS gives us 12 mem clocks per frame. At this point, 12.72 mem has already exceeded the 12 mem threshold. We can also look at FPS. Initially, the system can maintain 60 FPS because the GPU can still handle the load. But around frame 2200, FPS starts to drop. because the per-frame clocks have exceeded the 12 budget required for 60 FPS. Interestingly, at around frame 3900, FPS drops sharply instead of decreasing gradually. Why does this happen? Because at that point, the GPU's maximum frequency suddenly drops from 720 MHz to 586 MHz, so the available compute capacity decreases, and FPS follows immediately with a sharp decline. In the early stage, when overdraw is still low, per-frame clocks are also low, and the GPU does not need to run at maximum frequency. As overdraw increases, clocks continue to rise. However, once the GPU stays close to its maximum frequency for a sustained period, clocks continue increasing and GPU pressure becomes extremely high. At this point, thermal or power constraints trigger frequency throttling, which leads to a sudden FPS drop. So in summary, FPS, GPU operating frequency, and per-frame clocks are tightly coupled and influence each other directly. Next, let's look at a real-world test case. This is the garden scene from the Unity 2022 URP demo, tested on a Xiaomi 8 device. The two charts below were captured using our God Online tool. One shows FPS, and the other shows clocks. On the Xiaomi 8, the GPU maximum operating frequency is 720 MHz. Now let's look at a specific frame we captured. In this frame, the clock's value has reached 102 million, or approximately 102 clocks. If we divide 720 by 102, we can estimate that under this workload, the frame rate can only be sustained at around 7 FPS. So this is fully consistent with the relationship we discussed earlier. For example, if we aim for 30 FPS, then the per-frame clocks must be controlled around 24 member, or 24 million per frame. But in this case, the scene already reaches over 100 clocks, so it is clearly impossible to achieve 30 FPS. In our Gears tool, we also have a GPU clocks metric that is aggregated per second, while what we saw in God Online is measured per frame. If we convert it into a per-second perspective, we can see that the peak value is roughly around 720 MHz. In other words, from a per-second clocks perspective, it does not exceed the GPU's maximum frequency limit. From this chart, we can confirm that in this test scenario, the Xiaomi 8 GPU is essentially running at full load most of the time. However, even under full frequency conditions, the frame rate is still very low, and in many cases far below the target. So when we see extremely high GPU clocks, we can actually use the relationship between per-frame clocks and FPS to quickly determine whether the GPU is overloaded and unable to meet the target frame rate. We also conducted the same test on Xiaomi 10. We can see that the Xiaomi 10 has a maximum GPU frequency of 587 MHz, which is lower than Xiaomi 8's 720 MHz. However, under the same scene, Xiaomi 10 can reach around 17 FPS, while Xiaomi 8 only reaches 7 FPS. At the same time, the per-frame clocks on Xiaomi 10 is about 34 member. This means that under the same visual workload, Xiaomi 10 actually consumes fewer clocks per frame. This demonstrates that across different devices and GPU architectures, the amount of work represented by the same clock's value is not identical. From this comparison, we can draw an important conclusion. We should not judge GPU performance solely by the maximum frequency. A higher number does not necessarily mean a stronger GPU. What really matters is the relationship between the actual per-frame clocks required by the same scene and the device's own maximum frequency. Therefore, when performing GPU pressure comparisons, we must always collect data on the same device. For example, during optimization validation, we run the same scene on the same phone and compare whether the clocks decrease before and after optimization. Only this kind of comparison is meaningful. If we compare across different devices, the results are not reliable or meaningful. You can also verify this relationship yourself. 34.4 multiplied by 17 is roughly close to 587, which is consistent with the overall calculation model. In Gears, we can also collect per-second clocks data for this case. We can observe that on Xiaomi 10, the per-second clocks are not always stably close to 587 MHz on every frame. However, under high load conditions, it can approach full utilization, and it will never exceed the GPU's maximum operating frequency. From this simple test and the URP demo case, we can clearly define the relationship between three key variables: per-frame GPU clocks, FPS, and GPU maximum operating frequency are mutually constrained. Based on this relationship, we can derive an empirical formula for GPU pressure budgeting. We multiply by 80% because we do not want the GPU to operate at full load for extended periods. So in practice, we try to keep per-frame clocks less than or equal to maximum frequency divided by target FPS multiplied by 80%. In this way, while still achieving the target frame rate, the GPU will not stay in an extreme load state. Typically, it will stay around 80% utilization, which is more favorable for power consumption and thermal control. In the GPU mode of GameOptim Online, we also provide a corresponding analysis curve. When the background turns pink, it indicates that the current sampled per-frame clocks has exceeded the threshold of maximum frequency divided by target FPS multiplied by 80 cents. With this metric, we can quickly determine what percentage of frames are GPU bound. Once we identify that certain segments exceed the threshold, the next step is to locate the root cause. GPU pressure analysis is typically divided into two stages, the vertex stage and the fragment stage. In the vertex stage, we primarily focus on triangle count, which is the most fundamental and intuitive metric. In the fragment stage, we focus on fragment shaded, which represents the number of pixels actually shaded. In GOnline, we provide a fragment shaded metric with the following empirical recommendations. For low quality, it should be kept under 10 million. For medium quality, around 20 million, and for high quality, around 30 million. Fragment shaded is mainly influenced by resolution and overdraw, while post-processing is a special case that combines both factors. Because post-processing is usually full-screen rendering, its overdraw is relatively low, but shader complexity is often higher, which has a more significant impact on overall cost. Therefore, in fragment stage analysis, we typically consider resolution, overdraw, and post-processing separately. Overdraw is already a well-known concept, and it can usually be visualized directly using editor tools. We have also introduced how to implement this before. Here we focus more on the impact of resolution and the additional clocks cost introduced by post-processing. When triangle count, resolution, and overdraw are all within reasonable limits, but GPU clocks are still high, we need to focus on shader complexity. In other words, when diagnosing high GPU clocks, we generally follow this order: geometry complexity first, then pixel fill, then resolution and overdraw, and finally shader complexity. For shader complexity, we have also previously discussed multiple optimization approaches, including how to use Gears frame capture to locate shader hotspots. In addition, for more precise measurements, Mali offline compiler can be used for further analysis and validation. Let's start by discussing triangle counts. In real-world projects, a very common question teams ask is, how should we control triangle count? What is the acceptable range? Is there any theoretical value or empirical guideline we can rely on? To explore this, we conducted a set of experiments to validate the problem from a data-driven perspective. Initially, we tried a more theoretical derivation approach, testing different devices to see what range of triangle counts they can actually sustain. The test setup was quite simple. We tried to minimize the impact of the fragment stage as much as possible. So we reduced the overall rendering resolution significantly and set the render scale down to 0.1. Under this condition, we can assume that fragment pressure is largely eliminated and the main bottleneck shifts to the geometry stage. Then, in a very simple empty scene, we continuously added spheres, gradually increasing triangle count until the frame rate could no longer stay stable at 60 FPS. Our evaluation criterion was, if FPS stayed below 59 for 100 consecutive frames, we considered that the performance limit had been reached, and we recorded the corresponding triangle count. The final results were somewhat unexpected. On Xiaomi 10, the system started failing to maintain 59 FPS at around 4 million triangles. On Honor V20, it was around 2.26 million. On Xiaomi 12, about 3.69 million. On Huawei Mate 40, around 1.39 million. There were some seemingly abnormal results. For example, Xiaomi 12 performed worse than Xiaomi 10, and Mate 40, despite being a higher-end device, also showed a relatively low threshold. So intuitively, this dataset does not look very reasonable. We believe there are two main reasons why the results are not scientifically reliable. The first is differences in device health status. In our internal test lab, we have multiple units of the same model. For example, Xiaomi 10 has 2 or 3 devices, and results can vary across them. Even on the same device, we run multiple iterations and take averages because each run naturally contains fluctuations, so device condition can significantly affect the final outcome. The second factor is the runtime state of the device. For example, the reason Mate 40 shows such a low limit can be explained later. This type of idealized experimental setup makes it very difficult to produce stable, reusable conclusions. In other words, trying to derive a universal maximum triangle count per device using this approach is not scientifically reliable. Now let's look at the actual runtime state of the Mate 40, which explains why its result is lower. This test data is also captured using GOT Online. In the highlighted region, we can see that the GPU frequency stays around 260 MHz throughout the test. During the Mate 40 test, the GPU is clearly not running at a high-frequency state. However, it still follows the clock's FPS relationship we discussed earlier. At the point close to frame drops, we can observe that it starts failing to maintain 60 FPS. The corresponding per-frame clocks is around 4.5 member. According to our formula, to sustain 60 FPS, 260 MHz divided by 60 is approximately 4.3 min clocks per frame. In other words, once per frame clocks exceeds approximately 4.3 ms, frame drops will begin to occur. From this result, we can see that it still matches the model we derived earlier. Returning to the core issue, it becomes clear that real device runtime conditions and actual GPU operating frequency have a major impact on this kind of theoretical triangle limit testing. Therefore, deriving a unified maximum triangle count purely from theory is not valid. To better answer the question of how many triangles should we target, we need to change our approach. Instead of theoretical upper bound derivation, we directly look at real production game data distributions. In Gears, we can collect GPU primitive data, which represents triangle-related metrics. A key metric here is input primitive, which refers to the number of triangles submitted from the CPU to the GPU. One important point during data collection is that GPU primitive is measured on a per-second basis. In our tests, we use devices with Mali GPUs, such as the Mate 40 Pro, for data capture. There is a key technique here. We lock the target game to a relatively stable 30 FPS state. On the Mate 40 Pro, most games can maintain stable performance at 30 FPS. Under this stable condition, if we divide the per-second primitive count by 30, we can derive the per-frame triangle count. For example, in one game, we observed a peak primitive value of 19.2 meton per second. Dividing by 30 FPS gives approximately 0.64 meters per frame. That is about 640,000 triangles per frame. Using this method, we can reconstruct triangle usage patterns across different real-world games. Compared to traditional approaches, such as using RenderDoc for frame capture analysis, which only shows single-frame data and requires a complex workflow, this method is much more scalable. With Gears, we can directly connect to the device and continuously collect runtime data. This allows us not only to observe isolated data points, but also to track how triangle counts evolve across different scenes. Therefore, this approach is much more suitable for analyzing real shipped games, and it can also be used to benchmark competitors and understand geometry workload distribution across different product types. We also collected data from several well-known live games. This includes large-scale titles such as anime-style turn-based RPGs. In high-quality mode, we observed a triangle peak of around 1.12 million. The value in parentheses represents the median level extracted from the curve, which reflects more typical runtime behavior rather than peak values. Overall, we collected a large amount of real-world game data. During collection, we focused on open scenes where the camera can rotate freely. Most of these games support 360-degree camera movement, allowing us to observe geometry changes from different angles. Based on these conditions, we recorded triangle counts across low, medium, and high-quality settings. We marked 2 of these products in green as they represent particularly well-optimized cases. In particular, one open-world survival game with a realistic art style consistently stays below 500,000 triangles from any viewing angle. This is an excellent level of optimization, especially considering that its visual quality remains very high. This shows that with strong optimization, it is possible to achieve high visual fidelity without requiring extremely high triangle counts. Of course, there are also cases like anime-style turn-based games, where triangle counts tend to be higher. All the data here is collected under a 30 FPS condition. If we switch to 60 FPS, GPU pressure increases significantly and thermal load becomes much more severe. In some games, even 30 FPS already represents a relatively heavy load. Moving to 60 FPS further amplifies that pressure. Based on this real-world dataset, we can derive an empirical guideline range. For high quality, we recommend keeping triangle counts within 500,000 to 600,000. Beyond this range, it becomes much easier to enter high load or thermal stress conditions. For medium quality, the recommended range is around 350,000 to 450,000. For low quality, around 200,000 to 300,000. Of course, there will be differences across game genres, so these values should be treated as empirical ranges rather than strict rules. Overall, for most games, keeping high quality under 600,000 triangles is a relatively safe and reasonable target. In real production, however, this target often requires negotiation between art and engineering teams. In many cases, artists may feel that it is difficult to achieve the desired visual quality under a 600,000 triangle budget. In such cases, trade-offs between visual fidelity and performance are inevitable. That said, we have also seen highly optimized projects that achieve excellent visual results with relatively low triangle budgets. So in summary, this section presents an empirical guideline for triangle counts based on real-world production data. Here we add another topic: how to analyze triangle culling under a fixed camera view, specifically the relationship between input triangle count and what is eventually culled. Using the same dataset as before, on Galaxy devices, we can collect input primitive data, which represents the total number of triangles submitted to the GPU. At the same time, we can also observe how many are visible and how many are removed through different culling stages. Overall, culling can be divided into three main categories. The first category is the most common one: backface culling. This is typically enabled by default in shaders, for example using cull back or cull front. The logic is straightforward. For instance, in a sphere, no matter the viewing angle, half of the triangles are always facing away from the camera. These triangles are naturally culled. This type of culling is usually counted under metrics like frustum culling primitives, and it is completely expected and necessary behavior. The second category is frustum culling. It is important to note that this is not exactly the same as CPU-side frustum culling. On the right side, we can see a typical frustum diagram. There are 3 red objects, 2 yellow objects, and 2 green objects, plus the near and far planes, 7 objects in total. Among them, the 2 red objects are completely outside the frustum at the CPU stage, so they are excluded from input primitive statistics. For objects that intersect the frustum, part of them lies inside the frustum and part lies outside. The portion outside the frustum will be counted under frustum culling. This is the part we want to minimize. In one of our past projects, we encountered a typical issue. The scene used a large number of road-like strip meshes. These assets are usually authored as a single mesh. The problem is that even if the camera only sees a small portion, the entire mesh is still submitted to the GPU, meaning all its triangles are included in input primitives. However, the GPU will later discard the parts outside the frustum. The issue is that before culling happens, all these triangles already go through vertex processing, including MVP transformations and interpolation. These computations cannot be avoided, which leads to unnecessary GPU workload. Therefore, this type of mesh structure should not be overused in a scene. At the same time, there is a classic trade-off here. Some teams intentionally use this approach to reduce draw calls. So in real projects, a balance must be made between draw calls and triangle counts. The third category is coverage culling. This occurs in the pixel stage, when triangles are extremely small, or when a mesh has a very high triangle count but is far from the camera. Its projection onto screen space may fail to cover any rasterization samples. In such cases, these triangles are discarded during rasterization. This is recorded as coverage culling. Mali's official documentation provides detailed explanations of this behavior. A high level of coverage culling usually indicates a structural issue. Either the mesh is overly subdivided or the triangle density is too high. At this point, we introduce the concept of rendering density to evaluate whether a mesh is over-detailed. Mali also provides a practical guideline. A triangle should ideally cover 10 to 20 pixels on screen. On average, around 15 pixels per triangle is considered a reasonable range. Another reference also notes that because vertices are shared between triangles, the effective number of vertices per triangle should not exceed 1.5 on average. Based on these two guidelines, we can derive a control range for vertex rendering density. We define a metric, the number of vertices allowed within a fixed pixel area. Taking 10,000 pixels as an example, and assuming an average of 15 pixels per triangle, we get roughly 666 triangles per 10,000 pixels. Combining this with the assumption of 1.5 vertices per triangle, we can further derive. Within 10,000 pixels, the total number of vertices should not exceed approximately 1,000. In other words, we arrive at an empirical conclusion. Vertex rendering density should be controlled at around 1,000 vertices per 10,000 pixels. Based on this derivation, we also implemented a corresponding mesh analysis tool in the GPU module of GoT Online. In the asset analysis section, rendering density is used to evaluate which meshes have excessive vertex load. We can filter out all meshes whose minimum rendering density still exceeds 1,000. Here, minimum rendering density refers to the lowest value observed across different frames and camera angles. Because objects move and camera views change, the density varies per frame. So we take a conservative approach. Even in the most favorable viewing condition, if the density is still above 1,000, the mesh is considered consistently over budget. Such meshes can generally be classified as heavy assets. For example, a model named Suji has 2,729 vertices and a corresponding rendering density of 2,123. According to our target, it should ideally converge toward around 1,000. From this, we can estimate an optimization ratio of roughly dividing by 2.9. After optimization, its vertex count would be reduced to approximately 1,000. With this approach, we can quickly identify which models are over-designed in terms of vertex count and how much they should be reduced. This concludes the complete workflow for triangle data collection, culling analysis, and evaluating whether a mesh is excessively heavy. Next, let's look at a very critical factor in the fragment stage: resolution. With continuous improvements in mobile hardware, we're seeing devices with very high screen resolutions, some already reaching 3000 x 1400 or even higher. If we render strictly at native resolution, the fragment workload can increase significantly, especially in terms of overdraw and pixel fill cost. Let's start with a simple comparison. A traditional 1920 x 1080 resolution contains about 2.07 million pixels per frame. But on high-resolution devices such as Redmi K50 or iQOO 11, if we apply no rendering constraints and keep everything else unchanged, the pixel workload becomes roughly 2.3 times that of 1080p. This means the overall fragment stage pressure increases almost proportionally. So for these devices, resolution control becomes essential. Many teams say they want to keep render scale equals 1.0 at highest quality, meaning fully matching native resolution. However, if we follow this strictly, GPU cost becomes extremely high on high-resolution devices and quickly becomes uncontrollable. So we need to redefine what 1.0 actually means. We generally recommend that at highest quality, the actual rendered pixel budget should not exceed the 1920 x 1080 baseline. In other words, 1.0 no longer means native resolution, but instead means target pixel budget. Under this definition, we need to apply a scaling based on screen area. For example, the Redmi K50 has a resolution of 3200 by 1400, which is significantly higher than 1080p in total pixel count. In this case, if we still want the highest quality mode to align with a 1080p pixel budget, we need to scale render scale down accordingly, which is roughly around 0.68. There is also another case. Some devices have a screen area smaller than 1080p. In that situation, we should not upscale rendering blindly. Instead, we apply a clamp, taking the minimum between the computed scale and 1.0 to avoid unnecessary supersampling cost. Once this new definition of 1.0 is established, we can move on to quality tiers. Typically, high quality is 0.9 to 1.0 of the baseline, medium quality is 0.8 to 0.9, low quality is 0.7 to 0.8. This is a general empirical range. In addition, starting from Unity 2022, UR has integrated FSR, Fidelity FX Super Resolution. Its core idea is to render at a lower resolution and then perform high-quality upscaling, reducing cost while preserving visual quality as much as possible. This feature can be enabled directly in the player settings of Unity 2022. However, it is important to note that after enabling FSR, we can observe additional draw calls in frame debug. These passes usually involve relatively expensive shaders, which introduce extra GPU overhead and may even increase GPU clocks. So after enabling FSR, we cannot simply assume that lower resolution equals better performance. We need to rebalance the system. The key question becomes, how much should we reduce render scale to offset the additional cost introduced by FSR? Let's look at real test data. We performed comparisons on Honor V20 and Xiaomi 10. In the original project, the URP asset render scale is set to 0.8. On the V20, without enabling FSR, GPU clocks is around 1077. When FSR is enabled while keeping render scale unchanged, clocks increases to about 1292, roughly a 20% increase. If we then try to compensate by reducing render scale, for example from 0.8 down to 0.6, we find that GPU clocks stays close to 1077, with no meaningful improvement. In other words, in this case, a reduction to 0.6 is not enough to offset the additional cost introduced by FSR. Only by further reducing resolution can we actually bring clocks down, achieving a net gain and reducing overall GPU pressure. However, the situation is different on Xiaomi 10. On that device, after enabling FSR, the increase in clocks is not significant, so a moderate reduction in render scale is enough to produce a clear decrease in GPU clocks. This leads to a key conclusion. The performance impact of FSR varies significantly across different GPUs and devices. Therefore, there is no universal optimal render scale setting for FSR. The correct approach is to benchmark device by device using GPU clocks measurements to find the balance between FSR enablement and resolution scaling. In summary, both fragment resolution control and FSR strategies must be tuned per device rather than relying on a unified configuration. Alright, let's move on to another very important part, the impact of post-processing on GPU clocks. We'll go directly based on real test results. The test device is an Oppo R17, using a set of built-in URP post-processing effects, and we observe how they affect clocks. First, the first row is the empty scene baseline. Under full-screen rendering of an empty scene, it already shows about 1.9 menon clocks per frame. It's important to note that during the test, the GPU's maximum frequency is around 430 MHz. When we enable post-processing, we can clearly see that clocks start to increase significantly. And all the post-processing effects below are evaluated under the condition that post-processing is enabled. Let's first look at a very typical comparison, TIA low versus TIA high. In low mode, clocks is around 12.6 MHz per frame. In high mode, it increases to 17.4 MHz per frame. We also compare this with the FPS curve. In TIA low, the system can stably maintain 30 FPS. The reason is simple. 12.6 MHz is still below the threshold of 430 divided by 30, which is approximately 13.3 MHz. In other words, it is still within the GPU budget we derived earlier. However, in TIA high, 17.4 MHz already exceeds the 14.3 MHz threshold. As a result, FPS drops to around 25 FPS. This behavior is fully consistent with the clock's FPS relationship we established earlier. From this test set, we can draw several clear conclusions. First, if a project does not require post-processing in low-quality mode, post-processing must be completely disabled. We often see cases where teams define no post-processing in low quality, but the post-processing volume is still enabled in practice. This results in GPU cost with no visual benefit. It is pure waste. So the rule here is, if you don't use it, turn it off completely, not just reduce its impact. Second, the difference between bloom variants. Bloom high and standard bloom usually have very small visual differences, but the performance gap is significant. Therefore, Bloom High is not recommended in performance-sensitive scenarios. Third, tone mapping, especially ACEs. One important point here, ACEs is significantly more expensive under LDR conditions. From our tests, using ACEs in LDR adds about 3.7 Menor clocks per frame compared to HDR. Whether ACEs follows the HDR path in URP depends on two conditions. First, HDR must be enabled in the quality settings of the URP asset. Second, HDR must also be enabled in the post-processing settings. Only when both conditions are met will ACEs follow the standard HDR pipeline. If it runs in LDR mode, a large portion of tone mapping computation is executed in the post-processing pass, which significantly increases shader complexity, especially on high-resolution screens, resulting in higher GPU cost. Therefore, if ACEs is used, a fully enabled HDR pipeline is required. Otherwise, it is recommended to switch to neutral tone mapping to avoid unnecessary overhead. Next, let's look at anti-aliasing comparisons. We tested FXAA, MSMSAA, and TAA purely from a GPU clock's perspective, without considering bandwidth and other factors. The results are as follows. FXAA and MSA2 are relatively close, at about 7.2 men and 7.8 men per frame respectively. SMAA is around 11.2 meta per frame, with little difference between low and high modes. 4x MSAA is also close to SMAA in cost on this device. TAA is significantly more expensive, about 12.6 memers in low mode and up to 17.4 mem in high mode, making it the most expensive option overall. TAA also shows a noticeable difference between low and high modes, indicating that its internal computation is inherently more complex. Finally, there is a subtle but important observation. MSA4 and MA8 show nearly identical results. At first, this looks unusual, but further investigation shows that Oppo R17 does not actually support MSA8. As a result, Unity automatically falls back to MSA4 at runtime, and the same execution path is used. This is an important engineering takeaway. Different devices support different graphics features, and Unity will silently apply fallbacks, even if this is not obvious from configuration. Overall, this section shows that by comparing post-processing and anti-aliasing clocks, we can systematically evaluate which effects must be enabled at each quality level, which can be replaced, and which combinations will directly cause GPU overload. This is a very direct and practical way to use clocks as a metric for GPU performance diagnosis.